Okay, so in this lecture I want to carry on talking just about the classical statistical mechanics of frustrated magnets, but I want to get to some more specific points. And there are really three things which I want to cover, which are all to do with the issue of how you treat these frustrated systems theoretically. So at least to begin with, we should consider some of the simple approximations that we're used to using in other systems. And as far as the statistical mechanics of spin systems goes, the most familiar approximation of all is mean field theory. So I want to spend the first section of this lecture talking about what the difficulties are that come up when you try to use mean field theory. And as you'll see, there are serious difficulties which mean that mean field theory is not very useful at low temperatures. And then in the middle part of the lecture, I want to talk about an alternative approximation which is not much more complicated than mean field theory, called the self-consistent Gaussian approximation. And this is, I think, a nice thing to know about, because in a lot of situations, it gives you a very good approximate description of correlation functions and so on. So for example, if you have an experiment on some appropriate material that you can think about classically, it may actually be the best way of doing a calculation. But it's also not very systematic, and you can't see where it would go wrong and so on. So ultimately, we'd like better methods. And at least as theorists, what you mean when you say a better method is often something which you can say in some sense is correct at long distances, or long distances and low energies if you're discussing a quantum problem, which I'm not. And in frustrated magnets, when we look for descriptions that are correct at long distances, we often end up with what are known as Coulomb phases. And what I'll describe in today's lecture is a version of that in the simplest setting, which is the triangular lattice Ising model, which I think brings in a lot of ideas that will also be useful when I talk about spin ice tomorrow morning. Okay, so to get started, I want to talk about mean field theory, and just to make sure that we're seeing things in the same way, let me remind you of some definitions. So in general, we want to calculate thermal averages, and a definition of what we mean is that we have the Boltzmann factor. Is this me? So a definition of what we mean by mean field theory, well, the starting point would be what we're trying to calculate exactly, and we have a Boltzmann weight, and then some quantity, some observable, and a partition function as a normalization. So this we could write as an expectation of whatever the observable is. And then the idea in mean field theory is that we replace this with a trace of an approximate Hamiltonian, which we can write as angular brackets with a 0 underneath to mean approximate. And then in order that the thing on the right we can calculate explicitly, we take this to be some single site Hamiltonian, perhaps with some effective exchange field in it. And then the central result is that the free energy of the system we're interested in is bounded from above by the expectation of the Hamiltonian in this approximate thermal average less temperature times the entropy in the approximation. And then you choose the single site Hamiltonian so as to get the lowest upper bound on the free energy. So if you work that through, then we don't need all of the details, but if we think about the contribution from the Hamiltonian, then we get interactions multiplying the site magnetizations. And if we think about the entropy of a spin in this single site approximation, then we have some constant term that won't be important. And as we increase whatever exchange fields there are in this Hamiltonian, and therefore increase the magnetization at the sites, the entropy decreases, so we end up with some positive term involving the square of the magnetizations, and so that has a coefficient which is some constant times kT, and involves the sum of the squares of magnetizations. And then if we expand this entropy at higher order, we get terms which are fourth order and so on. Okay, so that's the general structure of mean field theory. And then you say that you should choose the exchange fields that are in this single site Hamiltonian, and therefore the values of the magnetization, in such a way as to minimize your estimate for the free energy. So that final step is that we pick these MIs to minimize the right-hand side. And then two kinds of things can happen. If we're at high temperature, then this term, which has temperature as a coefficient, is going to be dominating, and the minimum for the free energy will be when all these magnetizations are zero. Right. Well, first of all, it's a single site term, so it should be a square of contributions from each site. And then in the single site Hamiltonian, we have some exchange fields, but whatever they are, we're parameterizing their effect in terms of the magnetization. So we can do some kind of Taylor series expansion, and the odd terms, I think, will vanish by symmetry. And what we do need is that the coefficient of the quadratic term should be positive, and the factor of t comes from this prefactor here. And it's positive because as we turn up the exchange fields and induce a non-zero magnetization, we reduce the entropy, and the entropy is coming into this expression with a negative sign. So that's the sequence of arguments. Any other questions? So when we ask what exchange fields, and therefore what magnetization minimizes the free energy. At high temperatures, it's pretty clear that we have zero magnetization. That's the paramagnetic phase. But you also expect that you may be able to get a different phase with non-zero magnetizations. So what usually happens in mean field theory is that below some critical temperature, we have MIs which are not zero. And of course, the critical point comes from looking at the eigenvalues of this quadratic form and asking when the lowest eigenvalue changes sign. So in general, the eigenvalues of the exchange matrix, some of them will be positive and some of them will be negative, but we're interested in the smallest one, so we're interested in the negative one. And so we'll get TC from the smallest eigenvalue of that term, so let me call that E min, plus this term, C KB TC, being equal to 0, and this is negative. So mean field theory will correctly, mean field theory will give you a supposed value for the critical temperature, which is set by the smallest eigenvalue of the exchange matrix, which will be of order the Curie-Weiss constants that we were talking about in the lecture this morning. And the message from experiment, looking at that graph of susceptibility against temperature for the material SCGO, was that nothing actually happens on the temperature scale set by the interaction strength. So if we go further and ask what else mean field theory tells us, then below the critical point, the M's settle into a pattern in an unfrustrated system that shows long-range order. And within this calculation, the way that you identify the pattern is that the M's settle into the eigenvector corresponding to this smallest eigenvalue of the interaction matrix. And the eigenvector of Jij corresponding to this epsilon min gives us the ordering pattern. And it's going to turn out that it's at this point that we see how mean field theory goes wrong in frustrated systems. So to have a reference point for comparison, let's think first of all about an unfrustrated system, and for example, square lattice with nearest neighbor interactions between on the square lattice. And then, of course, because we've got translation invariance, we can diagonalize the interaction matrix by Fourier transforms. And what we get in that case is a J of Q, which is J times cos of Qx plus cos of Qy. So if J is positive for antiferromagnetic interactions, it has a minimum. That's this E min that I'm talking about, which is at qx equals qy equals pi. I'm working in units of the lattice spacing. The crucial thing here is that this is unique apart from the symmetries of the lattice, which gives us similar points at minus pi, and so on and so forth. What we find that's different in highly frustrated lattices is that the minima of Jij form flat bands. So in other words, you have a macroscopic degeneracy. And you can see that that's generally going to be true for the corner-sharing lattices that I was discussing this morning. If you think about the eigenvalue problem there. So if we take a corner-sharing lattice and consider I write the exchange matrix like that as a matrix, and if we consider that with phi some fixed length vector, then by the variational theorem, this is an upper bound on E min. But on these lattices made out of corner-sharing clusters, we can write. Yes.
So only if written J, Mi, and J.
Yeah.
Now it's a matrix structure that derives from the sublattices of the lattice. So now this is a matrix, right? So this is 5.
Yeah, so it's a matrix whose elements are Jij.
Just the dimension of the matrix is the size of this.
The number of sites in the system, yes. And it's true that there are then some things to say about the translational symmetry and the number of sites within the unit cell. So I was going to say them in a moment, but let's talk about that now. In a translation invariant system, you expect to be able to block diagonalize this matrix using the translational symmetry, and then the block will have size, the number of sites within a unit cell. So in the example of the square lattice, block diagonalizing it reduces it to 1 by 1 blocks, but in the case of these other lattices, you'll have a block size which is the size of the unit cell. So on the Kagame lattice, you have 3 bands, and on the pyrochlore lattice, you have 4 bands corresponding to the number of sites in a triangle or a tetrahedron. Okay, so the idea is that from the variational theorem in linear algebra, we can get an upper bound on the minimum eigenvalue, and then using the same ideas that we talked about for spin systems, we can say that if Jij is simply J for nearest neighbors on one of these corner-sharing lattices and 0 otherwise, we can write this thing as J times the sum over clusters of the square of the sum of sites within the cluster of phi I squared. And then we get some diagonal terms here which are not included there, but they just give us a constant. So So what we get from this is that the minimum value of this quantity is achieved when the sum of the phi's over the sites on every cluster is 0. Okay, so again, the logic was that below the apparent ordering temperature that comes from mean field theory, we'd like to identify the ordering pattern, and we get that by finding the eigenvectors of the exchange matrix corresponding to this minimum eigenvalue, and we can think about those eigenvectors in this way, and we discover that the eigenvectors with minimum eigenvalue on these lattices of corner-sharing units will be eigenvectors for which the sum of components within each frustrated cluster is equal to 0. And now we can do something like the Maxwell counting that I talked about before. So the number of degrees of freedom that we should be thinking about, well, the degrees of freedom here are the amplitudes of the eigenfunction on each site. So the number of degrees of freedom is the number of sites. And the number of constraints, well, if we want to be in one of the eigenvectors of the minimum eigenvalue, then, as I've said, we have to constrain the sum of components on each frustrated cluster to be 0. So the number of constraints is equal to the number of clusters. Yeah.
From that condition to the sum of clusters condition, so that's assuming that the interactions are all homogeneous in the cluster.
Yes, yes. Yeah, this is specific to that. Yeah, yeah. And if you break that condition in general, you'll select a particular ordered state. Yeah. Okay, and then, as I said this morning, in these lattices, the number of spins is Q over 2 times the number of clusters. So the degrees of freedom in the ground state, which now is the number of eigenvectors belonging to this minimum eigenvalue, is the number of degrees of freedom minus the number of constraints. And incidentally, I gathered from a question after the lecture that I wrote this with the opposite sign this morning. So if you were taking notes, you might want to correct the sign. But you should see that it's wrong what I wrote, because it gave you negative values, whereas this should be something positive. In any case, there are some type notes which I believe Raj has either already put online or will put online, and then you can use those to check the equations. So if we use this here, the number of degrees of freedom is Q over 2 minus 1 times the number of clusters. So if we look at the consequences of that, then on the Kagame lattice, as I was saying, translations allow you to block diagonalize the exchange matrix, and because we have 3 sites in the unit cell, we have 3 bands, so we should be plotting as a function of 2-dimensional wave vector, but I'll just plot schematically in one direction. So we have the different eigenvalues of this exchange matrix, which we can kind of label by J and some L, which tells us which band we're in. So again, the point is that translation invariance gives you a 3 by 3 matrix, and then you can diagonalize that, and you get 3 bands. And what we learned from this calculation is that, well, if we put q equal to 3 in here, we get we get 1/2 times the number of clusters. So the number of spins is 3/2 times the number of clusters. So sorry. Well, what we wind up with is the important point here is supposed to be that the degeneracy of the lowest band comes out to be extensive, and the way that works is that you have a band which is completely flat. Its eigenvalue is independent of wave vector, and then you have two dispersive bands which look something like that. And on the pyrochlore lattice, it's something similar. If you put q equals 4, then you get a higher degeneracy. So, in fact, on the pyrochlore, you get two flat bands and two dispersive bands. And now the point is that you see that mean field theory has failed because it's given you a suggested critical temperature on the order of the interaction strength, but below the critical temperature, it doesn't tell you what the system will do because there's this macroscopic number of modes which the magnetization apparently could condense into, and what it does instead, at least in a lot of systems, is fluctuate between the different modes. Okay, so then the next stage will be to go on and talk about a better approximation, but are there any questions about that first part?
For the pyrochlore, one of the flight band is the ground state manifold and the other flight band indicates what?
I think they're both part of the ground state manifold. So there are, if you look at the details of this Maxwell counting, then there are slight differences between what I was talking about this morning and what I've just presented. And the point is that this example that I've just presented is a really straightforward problem in linear algebra. And so the counting of degrees of freedom and constraints really tells you about the number of independent solutions. This morning, I was hiding some things under the rug because it's not really a problem in linear algebra because you have a nonlinear constraint, which is that the length of each classical spin is fixed. And so that changes the outcome from these Maxwell counting calculations to some extent. But I mean, that's why you may be seeing a factor of 2 difference between the number of states in the flat band here and the number of ground state degrees of freedom that I talked about before lunch. But basically, the states in the flat band do correspond to ground states. You just have to impose the fixed length spin constraint on them. what we're about to do. Sorry, but it
maps onto this way.
Yeah, with an important difference. Okay, so I mean, my logic is that if you come along to a problem in the classical statistical mechanics of frustrated magnets and look in your standard toolbox, the first thing you would think of using is mean field theory, and what I've tried to explain to you is that that will generally fail. And what I want to do next is tell you about something that's called the self-consistent Gaussian approximation, which is also very simple, but which gives you rather good results. And which will also use some of the things that we've been thinking about to do with the eigenvalues of the interaction matrix and so on. So to make sure that I'm clear about the general framework, when we talk about a trace in one of these classical spin systems, what we mean is that for every site in the system, we want to integrate over spin orientations, but these are fixed length spins, so we have a delta function which imposes that constraint. And the self-consistent Gaussian approximation is just an approximation that we give up on imposing this delta function exactly. And what we say we'll do instead for our trace operation is an integral over spin orientations, but now we just put in a Gaussian factor, which I'm going to write with a coefficient lambda over 2. And then this is the self-consistent bit. We choose the Lagrange multiplier here so that when we evaluate using this approximation the square of the spin length, we get 1, as we ought to if we impose the constraint exactly. So, of course, a question you might reasonably ask at this point is, are there circumstances where this is not an approximation? Can we introduce some kind of small parameter which will put things in control? And there's a well-known answer to that, which is, yes, it's exact if the number of spin components is large. So it's exact for n component spins as n goes to infinity, but it's actually useful much more generally. So if we make this approximation, then if we calculate some average within that approximation, we've got the usual normalization, and we've got integrals over the spin lengths, and now the components really don't play any role, so I'll stop writing component labels. And then what makes it all tractable, of course, is that we've got simply a Gaussian integral to do. We can collect all of the spins at the different sites together into some large spin vector, and then as some notation, I had this matrix J, let me write it, because I'm going to be thinking about systems with only a single coupling strength, let me write it as J over 2, where J is the single coupling strength, times a matrix A, which is known as the adjacency matrix, which has the property that it's 1 for nearest neighbors and 0 otherwise. And then this thing here I can write as beta, the inverse temperature, times J, times the adjacency matrix, plus, and then from this term I've got lambda times the unit matrix. And then it's a general result from working out Gaussian integrals that if I look at the correlator between spins at two different sites, Jij, it'll just be given by the ijth component of the inverse of this matrix. So it'll be the ij component of the inverse of beta j times A plus lambda times 1. And then in particular, if we think about this self-consistent condition which fixes the value of lambda, we should take the diagonal element here, and then if all the sites in the lattice are equivalent, we can simply sum over all sites and divide by their number. And what we have is then the self-consistent condition is that 1 is equal to 1 over n times the trace of beta j A plus lambda times the unit matrix inverse. So to actually get something from this in practice, for instance, if you were trying to understand some experimental data, you would use this expression to calculate correlation functions, and you determine the value of lambda self-consistently from this expression, and it really works quite well and reproduces, for example, Monte Carlo results. But in this context, probably the best thing is to think about what happens when we go to the low temperature limit. And if we go to the low temperature limit, obviously, beta gets very large. And what that means is that in this inverse, it's only the smallest eigenvalue of the adjacency matrix or the interaction matrix that contributes because we have a 1 over beta j factor suppressing the contribution from the other eigenvalues. So in the low temperature limit, SISJ ends up being proportional to something which is the projection operator onto the space spanned by the lowest eigenvalue of the interaction matrix. So it's a projection operator onto the flat band that I was talking about. So put slightly differently, what this is saying is that within the self-consistent Gaussian approximation, at low temperatures, the system doesn't order into any one of these eigenvectors of the interaction matrix. Instead, it fluctuates between all of them precisely because there's this macroscopic number of degenerate modes. I guess one final point to make, I had a picture before of the eigenvectors, sorry, the eigenvalues on the Kagame lattice, which shows the same kind of behavior as a lot of other lattices. So I had a picture which looked like this with a flat band and then some dispersive bands, and the dispersive bands become degenerate with the flat band at one point in Q space, and the eigenvectors have a singularity there, and it's that singularity which determines the long-range behavior of this projection operator, and it turns out to fall off as a power law. So, I mean, one could say more about the mathematics of that, but I'll be covering the same physics in different ways later on.
So you say that one is singular, and single DC match, or this target value, one is the lambda equal to 0.
What happens is that lambda, well, all right, this is the eigenvalue of the, well, not even the adjacency matrix, actually, the adjacency matrix plus a constant. So the key thing is that there's a flat band, and when beta j is large, you wind up projecting onto the flat band. And the value of lambda takes care of any constant that there is in the eigenvalue. Okay, so the ideas so far are that mean field theory doesn't work, but the self-consistent Gaussian approximation gives you a rather easy way of thinking about correlations. But at the same time, it's a kind of one-shot approximation, or if you like, it's only controlled when the number of spin components is large. And what we'd also like is some other tools, and in particular, some way of getting a controlled description of systems at long distances.
Suppose I consider a system where there's no order disorder, then is the 1 by n series controlled?
Yes, probably, but no one's ever worked that out in detail. There's a footnote in a paper by Roderick Mesner and Shivaji Sondhi where they promise that they're going to do the 1 over n calculation for the pyrochlore lattice. But it was about 15 years ago, and it hasn't been published yet.
does this calculation show that at low enough temperature, both the current length and high probability is power law?
That's correct. I mean, at non-zero temperature, you have a finite but large correlation length, and within this calculation, it diverges, I think, as, well, depends, it's probably different between the two, but it diverges as you go to zero temperature, and in the zero temperature limit, it's a power law, and inside the correlation length, it's a power law. Okay, so what I'm talking about now, for people who know the term, is really the physics of Coulomb phases, and that's relevant to spin ice, as I'll explain in a lot of detail tomorrow, but you can also illustrate a lot of the ideas in the context of a two-dimensional system, and I'm going to use the triangular lattice Ising antiferromagnet as the example. So you can say that probably the triangular lattice Ising antiferromagnet was the first highly frustrated magnet to be studied in detail. The point is that because it's an example of a two-dimensional Ising model, it can be solved exactly. And a few years after Onsager's exact solution of the square lattice Ising model, Vanier worked out some properties of the triangular lattice model. So the first results are from Vanier in 1950, and one of the things he realized is that there's no finite temperature phase transition, and of course, in principle, you can get correlation functions also from the exact solution, and I think this was not Vanier, but in later work, what we know from the exact solution is that the correlation functions go like r to the power minus a half as temperature goes to zero. So basically what I want to talk about is how you can get an understanding of this without following through the exact solution. Now, given where this is coming in my lectures, I'd better avoid some misunderstandings. So, of course, I've been talking about systems with flat bands, and if you diagonalize the exchange matrix for the triangular lattice, you'll soon discover that you have a discrete number of minima in the Briand zone. So this is not a system that's frustrated in that sense. And in fact, if you study XY or Heisenberg spins on the triangular lattice, then you'll find that there are Néel ground states. So you might be guided in a misleading direction from that point of view. But when you consider the Ising model, you can quickly see that it has exactly the sort of ground state entropy that I talked about this morning in relation to the pyrochlore Ising antiferromagnet. So just to avoid confusion, I should say that, in fact, there's no flat band, and we need, so there's order for XY spins, but degeneracy for Ising spins. So if we think about the ground states, going back to things that I started with in this morning's lecture, I said that to find ground states in these systems of frustrated clusters, you should minimize the total spin in the cluster. And if we have 3 Ising spins which have values either plus or minus 1, then obviously we can't get a minimum value of 0. We have to have either 2 spins up and 1 down, or vice versa in every triangle. But if you think about possible configurations of spins, then you quickly realize that there are situations which give you high degeneracy. So let's think about a hexagon and the site in the center, and suppose that we have alternately around the hexagon spins which are up and down. Then in the center, because 3 of the neighbors around the hexagon are up and 3 are down, we have vanishing exchange field. And so this central spin can be up or down in the ground state. Sorry, was there a question there? No. So you can imagine a finite density of flippable spins, and that gives you a finite ground state entropy. Okay, so now the point is that we'd like a more convenient way of specifying whether a spin configuration is a ground state or not than by checking that each triangle has 2 spins in one orientation and 1 in the other. And there is a nice way of doing that, and it's by mapping spin configurations onto what's called a height model. So the basic idea is that we can go from a spin configuration to a height field, and the condition that the spins are in a ground state is the same thing as saying that this height field, which I'll define in a moment, is single valued. And of course, the idea that a function is single-valued is something which is rather simple to state and much easier to think about than this ground state condition. And then, crucially, it's something that we can keep hold of even if we try and coarse-grain our description of the system and think about it in some long wavelength way. So how does this mapping go? Well, there are two steps. The first one is a bit of bookkeeping. We need some convention to give the bonds on the lattice an orientation. So on the triangular lattice, I have triangles which are pointing up and triangles that are pointing down. And I can say I'll go anti-clockwise on the up triangles. And then I say that the height difference when I go from one side to the next, or rather I should say, first of all, I define heights on the sides of the lattice, and the height difference is going to be +1 if I have an unfrustrated pair of spins on the bond I'm traversing using this orientation convention. And so with antiferromagnetic interactions, unfrustrated bonds have opposite spins. And I'll say I have a height difference of -2 if the spins are frustrated. No, so at the moment the heights are defined on the sides. There's going to be one more step, but so I'll keep this, but so what I mean is that if I have an up triangle, then my orientation convention is to go like that. And if I start with this spin up and I say that I have a height h at the top of the triangle, and if this spin is down, then this bond is unfrustrated, so the height goes up to h+1 here. And then if this spin is up, I go up to h+2 because this bond is unfrustrated. But then I have two parallel spins, which is a frustrated bond because I haven't minimized the energy of an antiferromagnetic interaction. And so now I have a height difference of -2, and that takes me back to h. And the crucial thing is that getting back to h is the same thing as saying that this triangle is in a ground state. So if I apply that to the triangle that I've drawn, then I can fill in some heights. And so if I take this triangle to be h, then that's h+1, and then if the circulation on this triangle is anti-clockwise, on the down-pointing triangle, it has to go clockwise to be consistent with my bond orientations. So when I go across this bond, it's unfrustrated, but I'm going in the opposite direction to my convention. So I step down 1 unit, so the height here is h again. And then this is a upward pointing triangle, so I go around it clockwise, so the height here is h plus 1, and then here I go down to h, and here it's h plus 1. And it's worth contrasting that with what happens in a situation where I haven't arranged for this high degeneracy from the flippable spin at the center. So if I take an arrangement with, say, a line of up spins in the top row and down spins in the middle row and up spins in the bottom row, then again that's a ground state of the triangular lattice because each triangle has two spins with one orientation and one with the other. But now this spin in the center is not free to flip because it has four neighbors which are up and just two neighbors that are down, so it has a net exchange field which determines its orientation. And if I work out the heights, then I find a height of h plus 1, h, and then I think it turns out to be h minus 1 here, h minus 2, h minus 3. And the point is that in this example, the height fields only have small fluctuations, and so we can say this is roughly flat, and it also has a high entropy because of the flippable spin. And this has an average gradient. In fact, it has the maximum possible gradient. So it's certainly tilted, and it's got no entropy. And the idea is that we can use these differences to write down a coarse-grained or approximate Boltzmann weight for configurations of the height field, and use that in the hope of getting a long wavelength description of the low temperature states of this model. And there's one point which is worth making at this stage to do with where we define the height fields. And there was a question just now about whether the height fields are defined on the original triangular lattice or on the dual lattice. And you can see that as we go around one of these triangles, the height field steps up or down on each bond. And it would be convenient to get rid of those fluctuations. And we can do that by defining a height at the center of each triangle, which is the average of the three at the corners. And if we do that, then this configuration turns out to give us a completely flat valued height field. In other words, you get the same value in the center of all triangles, and this still gives us a tilted height field because when you do these averages, there are clearly going to be differences between the different triangles. So that's a detail which it's maybe not worth stressing. The key thing is that if we coarse grain, we're going to want a continuum height field anyway. So when I say continuum field, there are really two aspects to that. So one is I forget that the space label originally lived on a lattice. And then the other thing is that as I define things, the height field took values over integers, and now I'm going to allow it to take values over the real numbers. And the conjecture is then going to be for the statistical distribution of this height field. So what we want to do is write down a functional that gives us the probability distribution of this height field. And because we think in the language of statistical mechanics, we think of that functional as being related to a Boltzmann factor. And the idea is that, from the two examples that I showed you, there's more entropy of ground state fluctuations when the height field on average is flat. So what we want to do is write down something that penalizes gradients in the height field. And the easiest way of doing that, consistent with symmetries, is to write down a term like that. And what we should do then is think about some consequences. And to think about consequences, we need to be able to go not just from the spin configurations to the height field, but from the height field back to the spin configurations. And yes.
So earlier you drew two configurations, one which was flat and one which had noise possibility.
Yeah.
We both allowed configurations within the ground state.
Yeah.
Nevertheless, we're penalizing one or the other because of the entropy gain. Is that right?
Yes, thank you. So, yeah, so this is a very important point to stress. So we're thinking entirely at the moment about ground state configurations, and we want to be able to calculate averages over all the ground states. And if we were sticking with a microscopic description, we would simply do a sum. But the whole idea of coarse graining is that we want to imagine summing out short-distance fluctuations and having some effective theory for the long-distance description. And so the idea here is that we can integrate out short wavelength fluctuations in the height field, and that will give us this conjectured form. So it's because the short wavelength, the entropy of the short wavelength fluctuations is higher if the average gradient of the height field is small. That's what leads us to a form like this. So to think about consequences, you would like to be able to go from the height field back to the spins, and maybe there are some aspects of this which I'm getting a bit short on time to go over in detail, but let me write down the result at least. So you can say that the spins are given in terms of the height field by a cosine and this phase is either naught or plus or minus 2 pi over 3, depending on sublattice. And to justify this, you have to take the rules that I gave for going from a spin configuration to a height field and follow them through in the reverse direction. And I think for the moment, the final result is something that's simpler than the details of the argument that get you there. So maybe I could just state that and leave that as something for you to check through. So then the sort of question which you can ask using this height model description is, what should the spin correlations be according to the description? And so what we want to do is calculate an average over a product of two of these spin operators using this probability distribution. So we can separate the cosine into two complex exponentials. And one thing that you see incidentally about this probability distribution for the height field is that it's invariant if we make a uniform translation of the height field. And that means that when we work out this average, the terms that contribute will be ones where we take a positive exponential from one of the cosines and a negative exponential from the other cosine. So what we end up with is something that's the average of and here I'm taking a case where the sites at the origin and at R are on the same sublattice so that these phases cancel. Okay, so what we want to do now to work out this correlation function is to average this exponential with this probability distribution. And the nice thing is that at this stage we can do the calculation exactly because everything is Gaussian. We've got just a quadratic theory here, and we've got a linear term there. And in fact, it's a general result about the average of Gaussian distributed variables that the average of this exponential would just be the exponential of half times the average of the square. So this is, in fact, just e to the, and then squaring this, we get a minus sign, so it's minus pi squared over 18 times the average of h of r minus h of 0 squared. Now, this average is something that you can calculate from this theory quite easily by separating into Fourier components. And when you do that, you find that the average that's inside the exponential varies like a logarithm. And when you take it into the exponential, what you get then is a power law. So what you find is that this falls off like r to the minus pi over 18k. And so the calculation or steps that take you from here to there are reasonably simple. And if you're following the details of this course and wanting to do the calculations, you should try and work that out yourself. And if you get stuck, just ask me. I have some notes and I could send them to you or go through it in one of the breaks. So what do we get from this? Well, we find that we've got power law correlations, and we find that the power in the exponent depends on really the only parameter that we had in the model, which is what's called the stiffness. Which you see is a dimensionless quantity. And as I mentioned, we know from the exact solution that this exponent should be a half, and so we can identify the value of the stiffness. So we can find this by we match this to the long-distance behavior of the correlation function. Okay, so at that stage you might feel that we haven't got very far because although we've introduced an effective coarse-grained description of the ground states, it involved this free parameter, and the only way that we had of finding the value of this free parameter involved taking a result from the exact solution. But actually, once we know this free parameter, we can understand quite a lot more about the model, and in the remaining few minutes, I'd like to sketch two of those things.
Question.
Yes?
Is there any way to derive it? Derive the value of K in this case?
No, I think the problem is that it really is a microscopic quantity. And so if you went from the triangular lattice to some other lattice that had an equivalent degeneracy and a height model description, its value would change. Or if you go from two-state Ising spins to ones with more states, then you can preserve the height model description, but the stiffness changes. So the only way of finding its value is by comparison with some other calculation of the long-distance correlators.
But in some cases it's possible, right? If for the classical diamond model, we can also map it to a large model, right? In that case, I think that you can also derive K, or is that also?
Sure, you can derive it, but again, it's by another exact calculation. So it's, in that case, I think it's an exact calculation of the dimer configurations using Pfaffians. Yeah.
Another question. So, is there a way to sort of deform the original microscopic model so that you can change the value of K? So, for the triangular lattice, you get one particular value, right? Can I add some other terms to the Hamiltonian so that I can smoothly change K?
I don't know of a way of changing it smoothly, but if you vary from a two-state Ising model to an Ising model with more states, then you can change it in discrete steps. Okay, so two final points. So the first one is to do with approximations that we made in getting to this height model that you might reasonably be worried about. So I said that when we treated H as a continuum field, I meant the word continuum to be applied to two things. We forget about the fact that the sites were on a lattice, but also we forgot that H was integer valued originally. And so one thing that you should worry about is whether that's a serious approximation or not. So we can think about the consequences of discreteness in H. So in other words, we can ask what happens if we modify this weight, adding a term which is maybe something which favors integer values by putting in a cosine term. And so then you have a field theory of this quadratic theory perturbed by a cosine term. And so there are standard techniques which I don't have any time to talk about, but which allow you to do an RG calculation to find out whether this discreteness is important or not. And what you find out is that it's RG irrelevant if this stiffness is small enough. Roughly speaking, the point is that if this stiffness is small, we have big fluctuations of H, and if we have big fluctuations of H, then this cosine gets washed out, and it's irrelevant if K is less than pi over 2, and the identification that we had here was that pi over 18k was a half, so k was pi over 9. So in other words, it's smaller than pi over 2, so it's okay to ignore the discreteness. Okay, so that was one of the two things to talk about, and then the next thing, which will lead into points that I make about spin ice, is to ask about excitations out of the ground state manifold. So I built all this on the idea that the ground state configurations have 2 spins in one direction and 1 spin in the opposite direction in every triangle. So if we have an excitation out of the ground state, that means that we have some triangles in the system with 3 spins parallel. And so what we should do is ask us what the rule for mapping from spin configurations to height fields does in a situation like that. So if we have 3 frustrated bonds, that means that we have a triangle with 3 parallel spins, and the rule that we were using was that the height changed by -2 units when we go across a bond with spins parallel. So if the height is h there, then it should be h minus 2 there, h minus 4 there, and h minus 6 when we come back. So in other words, we end up with a kind of vortex in the height field. Now, if you compare the energy of a triangle with 3 parallel spins against the energy of a triangle in the ground state, then the energy difference is, in fact, 4J. So the density of these vortices at low temperature will be reduced by their Boltzmann factor. Now, as well as the energy cost of making these vortices, when we introduce a vortex into the height field, it may affect the degeneracy of the ground state configurations that contain the vortex compared with configurations that don't contain a vortex. And one use for the height model is to estimate what the change in entropy is. So the idea is that as we go around the place where the excitation is, the height field increases by 6 units. For example, if we place the excitation at the origin, then there must be a gradient in the height field as we encircle the origin. So the vortex is at r equals 0, then grad h must, well, if we go around the origin at a radius of r, then the height field increases by 6 units, so the gradient must be 6 over the radius of that circle, in other words, 2 pi r. So the entropy cost will be, well, we can work out the entropy cost from this Hamiltonian, so it'll be k over 2, and then we've got the integral, and so doing the angular integral, I get a 2 pi, and then I have a radial integral r dr, and from this I have 6 on 2 pi squared, and 1 over r squared from taking the gradient squared. So the important thing is that I have an integral dr over r, so that gives me a logarithm. I have some maximum and minimum as limits on this integral, and the minimum will be something like the lattice spacing, and the maximum will be set by the system size. And this entropy cost of introducing a vortex is also offset by the entropy that you can get from putting its core at all the different possible places in the system, which also grows logarithmically with system size. And according to the value of the stiffness, it might either be the entropy gain from different locations for the vortex core that wins, or the entropy cost that wins. And you can see that as k increases, the entropy cost is more likely to win. And there's a critical value of k corresponding to a Kosterlitz-Thouless transition. And you can use the value of k that we get from matching with the exact solution to decide which phase you're in. And what you discover from doing that calculation is that vortices are unbound. And
is that any amount of control of the system? When the vortices unbound?
Well, this is really purely an entropic calculation. So in the first instance, it applies at 0 temperature. And the way that temperature comes in is just via the Boltzmann factor associated with the core energy of the vortices, which determines their density. So
this conflicts with the Danier results that were in correlation to case.
So that's at 0 temperature. So what I wanted to say is that the vortices set a finite correlation length. And their density, as I said, was controlled by the Boltzmann factor. So their density gets low as you go to low temperatures, which makes the correlation length diverge. And there's one final point which I want to make, which one can illustrate by drawing pictures, but since I'm over time anyway, I'll just say it in words. But it's a simple idea, and you should take it with you for the lecture tomorrow. So the idea is to do with the number of vortices that you introduce into the system when you flip a single spin. And if you think about how the height field changes on some large contour that encircles the place where you flip the spin, then clearly the height field far from the place where you flip the spin is not affected by the excitation that you've made, so the height field must be single valued. But on the other hand, the flipping the spin has introduced a vortex, and in fact what happens is that a spin flip introduces two vortices, one positive and the other negative, one a vortex, the other an anti-vortex, and you can do further spin flips to separate these two vortices with no cost in energy and with a limited entropy cost that you can estimate in the way that I was describing. So you have a simple example in this classical system of an analog of fractionalized excitations. That's to say, you flip a single spin, and it turns out that you've introduced two independent excitations. And we'll be coming back to that idea several times, both for spin ice as a classical system and for quantum systems in my lectures and others. Okay, so I'm sorry for going over. I'm sure I should stop there. Thank you.